friends, in this video we are going to discuss about the exponential distribution. It is the continuous counterpart of the geometric distribution. The geometric distribution is the discrete probability distribution of the number of Bernoulli trials needed to get first success, while the exponential distribution is a continuous probability distribution used to model the time we need to wait before a given event occurs. Event can be either success, failure, arrival, etc. For example, how long we need to wait until a customer enters our shop? How long it takes before a call center receives the next phone call? How long a piece of machinery works without breaking down? All these questions concern the time we need to wait before a given event occurs. This type of questions can be answered in probabilistic terms by using the exponential distribution. It has graph like this. This is the random variable x. Here there is probability of x. Graph goes somewhere like this, from 0 to plus infinity. So firstly we will derive the Pdf of exponential distribution. By using Pdf we will find the MGF, then we will solve some problems. Exponential distribution is very strongly related to Poisson distribution. The relation between the exponential and Poisson distribution can be concluded by saying that number of events per unit time follows Poisson distribution, while the amount of time between events follows the exponential distribution. So we will derive the Pdf of exponential distribution by using the Poisson distribution. The main objective of this distribution is to get a distribution that predicts the amount of time until the first event occurs. The amount of time until the event occurs means during the waiting period not a single event has happened. In other words, it is equal to Poisson distribution with probability x is 0. We already know the Poisson distribution formula. If I substitute x as 0, then we will be left with e minus lambda. This is just during 1 unit time. Let us try to visualize this, then it will be much clearer. For example, I am taking a timeline like this. Now I am dividing this into small single unit time starting from 0. 1, 2, 3, 4. It goes like that till t. Now if you want to model the probability distribution of nothing happens during the time period t, till this time nothing happen, I am not looking just 1 unit time, but I am looking during the time duration t. So it is equal to probability of x0 in first time unit times probability of x takes 0 in second time unit times probability of x takes 0 in tth time unit. This is equal to saying e minus lambda times e minus lambda times e minus lambda, that is equal to e minus lambda t, because we are looking t time duration. Here the Poisson distribution assumes that event occurs independent of one another. That's why we could write like this. Finally, we have probability of x0 in t time units equal to e minus lambda t. So this is the probability of nothing happens in t time units. In other words, this is equal to saying probability that the waiting time until the first event is greater than t time units. So this is equal to probability of capital T greater than small t. Capital T is the random variable for the time until the first event. So this is the probability that waiting time until the first event is greater than t time units. So if I deduct this from 1, so it is the probability that waiting time until the first event is less than t times. So the CDF is given by 1 minus e minus lambda t. We know that if we differentiate the CDF, we will get the PDF. So PDF is equal to lambda e power minus lambda t. This is nothing but PDF of exponential distribution. We will talk more about lambda and other things at the end of this video. So next we will find the MGF of exponential distribution. The MGF of any random variable is equal to expectation of e power tx. In this case, that is equal to integration of e power tx times the PDF of exponential distribution, and x takes values from positive infinity to 0. Now I am going to apply some algebraic operation on this, so please note carefully. I am taking lambda outside, then e power minus x lambda minus t dx. Now I am dividing and multiplying by the same thing, lambda divided by lambda minus t, and I am multiplying as well. Now I am assuming y is equal to x times lambda minus t. This part can be written as this is also equal to saying this is nothing but gamma function, that is gamma 1. If instead of 1 here it is n, then it will be gamma n. So what is the value of gamma 1? It is 1 minus 1 factorial, that is equal to 0 factorial. So this whole term will become 1. So we will be left with lambda divided by lambda minus t. So this is the MGF of exponential distribution. Now we will differentiate this MGF and we will try to find what is the first moment, then second moment. We will use the quotient rule to differentiate this formula. So first derivative of moment generating function of exponential distribution is equal to 0 multiplied by lambda minus t minus lambda minus 1 all divided by lambda minus t square. This becomes 0. This becomes plus lambda. Setting t equal to 0, we will get 1 by lambda. So this is nothing but the first moment, that is the mean of exponential distribution. If I differentiate this function again with respect to t and setting t equal to 0, I will get the second moment. This becomes 0. If I set t equal to 0, then I will be left with 2 lambda square, lambda power 4, that is equal to 2 divided by lambda square. So this is the second moment. Basically the variance is second moment minus the square of the first moment, that is equal to 1 by lambda square. This is the variance of exponential distribution. In the similar way we can find the third moment, fourth moment. From there we can derive the formula of skewness and kurtosis as well. We are not going to do that all this year. Now we will solve one problem and we'll see how this is working. The question says that on an average the life of a particular computer is 10 years. It is assumed that the life is exponentially distributed. Then find the probability that a computer will fail before 7 years. So here we will use the formula of exponential distribution, that is f of x is equal to lambda e power minus lambda x. What is the lambda here? We know that the expected value of the exponential distribution is 1 by lambda and the value is given here, that is 10. It means lambda is equal to 1 by 10. So by substituting this value into the formula of exponential distribution and integrating from 7 to 0, we can get the probability that a computer will fail before 7 years. So we can put all these values into this formula. I can take this outside and I am integrating by substitution. So I am assuming u equal to 1 by 10x, then du dx is equal to 1 by 10, then dx is equal to 10 times du. I can take this 10 outside, so we are left with integration of e power minus u is basically minus e power minus u, then substituting the value of u, and x takes value from 7 to 0, so this can be written as what is the value of e power minus 7 by 10? If we calculate this value, it is coming around 0.4960. So 1 minus this value, we will get finally 0.50, something like that. So basically there is a 50% chance that a computer will fail before 7 years. So in this video we started by exponential distribution, then we connected with geometric distribution, how it is related to geometric distribution. Then by using Poisson distribution we derived the Pdf of exponential distribution. Then from the Pdf we derived the MGF, then we solved one problem.